In a remarkable breakthrough to reshape the landscape of clean energy, Chinese scientists have achieved what was once thought to be impossible. What is that? Well, China's experimental fusion reactor has now managed to maintain its scorching plasma for an unprecedented 17 minutes.
What if we could capture the immense energy of stars right here on Earth? China's experimental advanced superconducting Tokamak, East, has recently set a groundbreaking world record by reaching temperatures exceeding 70 million degrees Celsius, hotter than the sun, and sustaining them for over 17 minutes. This remarkable achievement brings us closer than ever to unlocking a clean, limitless energy source that could transform life as we know it. The success of this experiment is a major leap toward developing a stable and continuous fusion reaction, which could one day power homes and industries without the harmful impact of fossil fuels. By achieving this milestone, China has moved humanity closer to harnessing limitless clean energy, potentially revolutionizing global energy systems. Fusion, unlike fossil fuels such as coal, oil, or natural gas, does not emit carbon dioxide or other harmful greenhouse gases, making it a powerful tool in the fight against climate change. While renewables like wind and solar are clean alternatives, they are weather-dependent and require large storage solutions. Fusion energy, however, promises a stable and continuous energy supply without the need for backup fossil fuels. The East Fusion Reactor replicates the Sun's energy generation process using advanced technology and engineering. Shaped like a donut, this tokamak employs powerful superconducting magnets to confine superheated plasma, preventing energy loss and sustaining nuclear fusion. Inside its vacuum-sealed chamber, hydrogen isotopes deuterium and tritium are heated to over 100 million degrees Celsius, creating a plasma where atomic nuclei collide and release massive energy. To reach such extreme temperatures, East uses sophisticated heating methods like radio frequency waves and neutral beam injection. Simultaneously, superconducting magnets cooled by liquid helium ensure efficient plasma confinement, despite the challenge of managing ultra-hot plasma alongside ultra-cold components. East's success in sustaining plasma and achieving fusion conditions marks a historic step forward. As scientists continue refining this technology, humanity edges closer to unlocking the ultimate power source, a clean, continuous, and sustainable energy future. East showcases fusion energy's potential as a clean and virtually limitless power source. China's progress in this field could have significant geopolitical consequences. If China successfully commercializes fusion energy ahead of other nations, it would not only lead a transformative technological revolution but also influence future energy policies, gaining substantial political leverage as the world seeks alternatives to fossil fuels. The first country to achieve practical fusion power will reshape the global energy landscape and play a key role in international energy discussions. However, these developments carry major implications for the United States. If China secures dominance in fusion energy, it could set global technological standards, potentially making other nations, including the US, dependent on Chinese innovation, similar to the world's current reliance on fossil fuel exports from specific countries. This scenario poses concerns for national security, as energy independence often intersects with military and geopolitical interests. A leading position in fusion technology could shift global power dynamics, prompting the US to compete for influence in regions with developing energy infrastructure, such as Africa, South Asia, and Latin America. Additionally, fusion could become a central factor in climate negotiations, strengthening China's leadership in climate diplomacy. For the US, these developments highlight the need to accelerate fusion research, secure energy autonomy, and maintain a prominent role in clean energy and climate diplomacy. China's leadership in fusion energy could spark an economic and technological arms race, compelling the US to ramp up its research to remain competitive. Dominance in the fusion market would likely force the US to reassess its energy policies and invest heavily in emerging technologies to avoid falling behind. As fusion technology develops, it has the potential to disrupt traditional energy sectors, creating challenges for the US in adapting its infrastructure and retraining its workforce. Furthermore, concerns over technological sovereignty could arise, with the US needing to protect intellectual property and counter potential monopolization by China. From a national security standpoint, China's leadership in fusion energy may grant it strategic advantages not only in energy production but also in sectors like military capabilities and space exploration. Energy security increasingly intertwines with national defense, and if China gains control over a transformative energy source like fusion, it could influence energy diplomacy, particularly in conflict-prone regions where energy security is critical. The US would need to accelerate its fusion efforts, adjust foreign policies, and bolster energy innovation to maintain its global leadership. Despite China's remarkable progress, the path to commercial fusion remains fraught with challenges. The inherent complexity of nuclear fusion, which replicates the sun's energy generation process, demands extraordinary heat and pressure to overcome the repulsive forces between atomic nuclei. Sustaining fusion reactions requires plasma temperatures exceeding 100 million degrees Celsius, far hotter than the sun's core. While East has made significant advancements, maintaining such extreme conditions for extended periods remains a technological challenge. China, like other nations, relies on superconducting magnets to confine the plasma, which requires cryogenic cooling with liquid helium. Any malfunction in this cooling system could collapse the plasma, halting the fusion reaction entirely. The technical, financial, logistical, and political hurdles are substantial. Overcoming these obstacles will require careful navigation if China hopes to turn the dream of clean, limitless energy into a commercial reality. China faces significant hurdles in making fusion energy commercially viable. Fusion reactors must not only generate more energy than they consume, but also do so consistently and reliably. Achieving what is known as net positive energy, where the output exceeds the input, has proven elusive for fusion researchers globally. Currently, the energy required to heat the plasma and sustain the reaction surpasses the energy output, meaning fusion is not yet a practical solution for global energy needs. Even if China eventually overcomes this challenge, the infrastructure needed to support large-scale fusion energy generation is massive. Building fusion power plants involves high initial costs due to the advanced materials and technology required to construct reactors capable of sustaining fusion reactions. These costs will be a major factor in determining when fusion energy becomes commercially viable. China must carefully weigh the long-term benefits against the substantial financial investment needed to bring fusion power to the grid. A related challenge is China's ability to maintain a robust technological and industrial base for continued innovation in fusion energy. While China has heavily invested in research and development, it faces limitations in fostering a domestic ecosystem capable of producing the specialized materials and components necessary for fusion reactors. For example, fusion reactors require materials that can endure the extreme heat and radiation generated by fusion reactions. These materials are currently rare and expensive to produce. Furthermore, China's reliance on imported high-tech components for some aspects of its fusion research could expose vulnerabilities in its long-term efforts. Disruptions in the global supply chain, whether from geopolitical tensions or trade restrictions, could delay the development of fusion energy in China. Political challenges also play a crucial role in shaping China's fusion energy ambitions. While fusion technology offers enormous potential, its widespread adoption would have far-reaching economic, environmental, and political consequences. China's drive to lead the world in fusion energy could raise concerns among other nations, particularly those already heavily invested in competing energy technologies. The competition in fusion energy could lead to tensions over intellectual property, technology sharing, and access to resources. Countries such as the US, the European Union, and others with ambitious clean energy goals might view China's dominance in fusion energy as a threat to their own energy security and technological leadership. This could create a complex geopolitical situation, with China's drive to push the boundaries of fusion technology potentially sparking competition or even conflict with other major powers. International collaboration is vital for advancing fusion research, but it introduces uncertainties. While China has collaborated with the ITER, International Thermonuclear Experimental Reactor, project in France and other fusion initiatives. These partnerships bring their own diplomatic challenges. Fusion energy is considered a highly sensitive and strategic area of research, and some nations might be hesitant to share findings with China due to concerns over technology transfers that could have dual-use applications. China's historical approach to intellectual property and technology transfer has raised alarms among other countries, limiting its ability to access the knowledge and partnerships needed to advance fusion energy. Additionally, any diplomatic tensions or disruptions in global cooperation could slow progress towards achieving commercial fusion energy. Another challenge is the environmental and social impact of scaling up fusion energy technology. While fusion is often seen as a clean energy source with negligible carbon emissions, the materials needed for fusion reactors are not entirely free of environmental concerns. For example, the extraction and processing of lithium, a key material for fusion fuel, could have adverse environmental effects. Moreover, building and operating fusion power plants could have local environmental impacts, especially during construction. Therefore, while fusion energy promises a sustainable, long-term solution, China must ensure its commercialization doesn't worsen existing environmental problems or create new ones. Public perception and support for fusion energy development is another significant obstacle. While fusion has long been considered the holy grail of clean energy, public enthusiasm and investment in fusion technology can fluctuate. Many people may remain skeptical about its viability, especially after decades of promises without tangible results. For China's fusion energy efforts to succeed, it will need the support of both the public and the government. It's essential for the Chinese public to view fusion not only as a scientific breakthrough but also as a vital part of China's energy future. Lastly, scaling up fusion technology to meet global demand is a major challenge. Even if China successfully develops a working fusion reactor, deploying this technology on a large scale will take time. Fusion power plants are complex and require extensive infrastructure, including power transmission networks and specialized workforce training. Scaling fusion technology globally will require significant investment in workforce development, public-private partnerships, and coordination between governments and industry. This scaling process is likely to take decades, and China must carefully manage the transition from experimental reactors to large-scale commercial fusion plants. In conclusion, while China's progress in fusion energy is undeniably remarkable, the path to commercialization is filled with challenges. These challenges include overcoming technical hurdles and sustaining fusion reactions, addressing financial and industrial constraints, navigating political and diplomatic issues, and ensuring environmental sustainability. As China continues its pursuit of fusion energy, it must confront these challenges with a strategic approach. Only by addressing these obstacles head-on can China unlock the full potential of fusion energy and secure its leadership in the global energy revolution.